Okay, we are at lecture 5. I said at the end of last class that we would begin today with any questions that you have, whether it's content clarification or problems in the text, some mistake that I've made that unfortunately got left up there that we need to clean up, or web assign questions. So we actually don't have a lot of time for this and to get accomplished what we're supposed to accomplish today, but we can start with that mainly because I said we would start with that. Any questions? Festering questions? Lingering questions? No?
No, I have a question.
Yes.
On WebAssign 1.1,
Okay.
number 11,
Okay, can you tell me what it is?
well, all I have is my work down. I think it had to do with the surface area and putting it in.
As a function of volume.
Yeah, putting it in
Okay.
volume.
Yeah, I remember that
Oh, yeah.
type of question. So does anybody have a printout of that with you today? 1.1.
I remember the problem.
WebAssign, and it's problem 11. Go ahead.
It's represent the surface area of a cube as a function of its volume.
Okay, surface area in terms of volume, right?
Yeah.
All right, so everybody, is that it? You looked it up? Same thing? Okay. And it's a cube? Mm-hmm. Okay. So what do we know? Let's start with the volume of a cube. What do we know is the volume of a cube?
X cubed.
Okay, whatever the side is, cubed, so let's call it x. Okay, and over here to the side, what is the surface area?
6x squared.
Okay, so each face is x squared, right?
Yes.
And we've got 6 faces that are all the same dimensions, so 6x squared. All right, so let's work with this thing, and then we'll kind of come back to this one. And if we can find something to plug in there for x in terms of v, then we're in business, right? Because we want a surface area function in terms of volume. So somebody that had success, a couple of you didn't have success with this, probably not your turn to answer, but those that did have success, what did you do to start with this volume function, finish with a surface area function? X is no longer there. It's a surface area function in terms of v. Okay, solve for x. So using v equals x cubed, the volume of a cube, side cubed, what is that solved for x?
Cube root of v.
Okay, take the cube root of both sides, so that would be v to the 1/3 equals x. Is that okay? Mm-hmm. If you use cube root, that's fine. Same thing, different notation. Now to get our finishing solution, we want to come over here, and we now have surface area in terms of x, which is the side, but we do know what the side is. What is x equal to? It's the cube root of the volume. So we replace x with what x is equal to. 6 times what?
V to the 2/3.
V to the 2/3. So we have a surface area function. If it bothers you that it's SA, then just call it S, surface area. And if you want to write it as a function,
S of v.
you could write S of V. It is a surface area function in terms of the variable v. Is that okay? Does that work?
Can we leave it raised to 2/3 power? Would you want?
You could either do that or say it's the cube root, the quantity squared,
Right.
or square it and then take the cube root.
Okay,
So
it's okay if we leave it there?
as long as you enter it in with the notation that they want you to use. Anything else real quickly? Blair.
When we run into problems like this, if we don't know how to solve them, would you say it's wrong to look up on the internet how to solve that type of problem?
That's fine.
Okay.
But eventually, they're trying to get you some practice here in kind of manipulating one formula and then using the results of that to help you simplify or plug into another one. I mean, that's the goal. Now, if it's something that's not quite as familiar, like the volume of a cube or the surface area of a cube, I don't see any harm in looking up those formulas to kind of get yourself refreshed. But eventually, something this, I think, I don't want to make you feel bad if you didn't get it, but something this simple in terms of formulas, volume equals side cubed, that ought to be something that you shouldn't have to look up. And surface area equals 6 times the side squared, that ought to be something you shouldn't have to look up. But some others that we don't use so much, like the volume of a cone or something, to look it up, that's fine. Anything else? Pending any WebAssign or any other issue. Is this the one you were talking about, Blair, that you wanted to ask yesterday?
It's one of them, yes.
Okay. Do you have another one that's real quick?
I actually solved it last night.
Okay. I like those questions. You figure it out yourself. That's what's supposed to happen.
The Norman window.
Oh, okay.
That's the other one I figured
All right.
out.
Yeah, that's a little, that Norman window.
Can we
You've
go
got.
over that one?
Yeah, can we please?
Oh man, see, I could have ducked out of there, and we could have gotten out of there without. So you've got the window that's shaped like that, right?
Yeah.
And what do we know about it?
32 feet perimeter.
So we've got this window, and I don't know if they did they give you a little picture?
Yeah.
Okay. My picture won't be nearly as good. What do we know about this window?
The perimeter is 32 feet.
Perimeter is 32. Now that probably differed.
Yeah.
You may have had a randomized variable on your homework, so it may not have been 32, but since you said 32 first. And what do we know about the windows? Anybody have the problem number?
12.
12, same WebAssign, 1.1?
Yeah.
That kind of looks like we planned that, right? 11 and then 12 right down the page. That probably is not the case more than half the time in here. Perimeter is 32. What else do we know?
The bottom length is X.
This is X.
That's all I know.
Okay. And what's the question?
Express the area as a function of width.
We want area as a function of width. All right, I've done this before, so that's not really fair. Somebody that had success with this problem, how did you get this thing started? Chandler.
Yes, I got the equation for the half circle, the half circle.
Okay.
And then the equation for area of the rectangle on the bottom.
Okay. Sound like a plan? Split the window up into two pieces. And we've got this rectangular part. So area of the semicircle
One.
plus the area of the rectangle. We'll add them together. All right, let's start with the semicircle. What is it that we know about the semicircle?
1/2 pi x squared.
Okay.
Oh no.
You know, like pi.
There
you
we
know,
go.
like diameter
Caught your own
is half?
mistake, didn't you?
Oh, yep, I sure did.
Okay, now it is half. It's half the area of the circle, so I like that coefficient.
But is the diameter x?
The diameter is x, so this distance is x, just like this across the bottom is x. So the radius of the semicircle is
1/2.
1/2 x. So in terms of the radius, not this radius, but any radius, what's the area of a circle?
Pi r squared.
Pi times the radius squared. So we want pi times this radius, which
1/2.
is 1/2 x. Is that correct? Squared. So there's the area of the entire circle, pi times its radius squared, and we want half of that because it's a semicircle. All right, area of the rectangle. I think we got to do a little work on this. We know it's x by
X
something.
plus h.
That's kind of the work, right, to the problem. That's a little bit of work with the semicircle, but I think we have some other work to do to get the other dimension, the height of this rectangular part of the window. So they probably gave us something that's going to help with that. So the perimeter is 32. So across the bottom, let's go ahead and kind of build a little equation for the perimeter. So it's x across the bottom
2x times 2h or whatever.
plus, let's call this, what do you want to call it, height?
Yeah.
Let's call it h. So we've got an h over here and an h over here. So we've got two h's. And then we'll eventually, I guess, have to solve for h. And then we've got this, which is really not perimeter. It's really circumference, kind of half of the circumference.
Pi r.
Okay, the circumference, Blair, of an entire circle would be 2 pi r. So we have half of that circumference. So we have pi r. And in terms of this picture, what's the radius?
X, or 1/2 x.
Would be 1/2 x.
X.
So does that look like the entire distance around this Norman window? X across the bottom, h, half the circumference, and another h. And we know, according to the equation, that that is 32. So what do we need out of that equation? This is a very common problem in calculus, by the way. These problems are not just, well, let's throw that one in the list of problems because it'll keep them busy for 10 minutes. There's not a lot of busy work in these problems. So this, you will see this having direct carryover when we get to doing max-min word problems, optimization problems. You'll be doing this kind of stuff. Isn't that nice to look forward to? I can see all the excitement in your eyes. But it is kind of fun. I like them. Hopefully you'll like them too. We want to solve for 2h first. So take this equation, get rid of the x, get rid of the pi times 1/2 x, slide them over here. And then we've got 2h. And ultimately, we want to solve for h. So let's just divide everything by 2. It doesn't have to look real pretty. Now we know what h is. And so what is back up here to the area of the rectangular part of the Norman window? Isn't it just x times h, right? And I could write down h, but I'm going to have to do another step if I do that. So what is h equal to? So now we have an area function in terms of x. So let's, somebody that has the directions on this problem, what does it say? Write the area as a function of the width, and the width is x, right? So we have, so if you look through here to see if you're done, pi is fine, that's a number. X is the variable, that's what we want. Another x, another x, another x. So looks like we're in business. Now, could it be simplified? Yes. But at least we've got it in terms of x. So some of you have had quite a bit of calculus. Mark, I know that you've had quite a bit of calculus. Is this something that you'll see later in terms of an optimization?
Yeah, maxes and mins.
Right. Max and min is what he said. Max and min word problems. So you'll start with a problem. You want to do something with the area, maximize or minimize, and then you'll have another little equation off to the side that's going to help you make that a function of a single variable. Questions on that? Okay. Let's go to Appendix B. Appendix B deals with conic sections. Probably had conic sections before. Here is how they are formed. I know this looks like two cones, but this is actually a cone. This is a cone, and so is this. So cones have two pieces to them. They're called nappes, N-A-P-P-E. So in the two nappes of the cone look like this. If you slice through here with a plane such that it creates intersection with one of the nappes, you can form an ellipse. That's why it's a conic section. This ellipse could be formed in such a way that it's a special ellipse, which is a circle. We've already handled those. If you slice through here with a plane in this fashion, the intersection is parabolic. And if you slice through here with a plane such that it intersects both nappes of the cone, then we have a hyperbola. Now these equations, just to take a quick look at them now, they ought to look familiar to something in your mathematical past, but we will derive them, at least these two, and this we will say it's very similar to what we did here, so we'll kind of jump to the final equation. Does that look familiar? Equation of an ellipse? Okay. Let's see how familiar before we even start. Anybody remember what the A, how to recognize the A squared differently from the B squared? Yes.
The larger number?
It's the larger denominator. So that the larger denominator will be A squared. It doesn't have to come first. Doesn't have to come first because it's added, so you can commute the order and get away with it. Not the case over here, right? Because it's subtraction. So the term that comes first over here is important because the second one is subtracted, and subtraction is not commutative. And we'll derive these, so I'm just trying to get a quick look at it. How do you recognize the equation of a parabola as being different from that of an ellipse or a hyperbola?
No division. No denominators.
Okay, well, we could make denominators. What's the big difference?
You're multiplying.
X squared, y squared, x squared, y squared. Not the case
The A
here,
is the
right?
coefficient.
Yeah, we do have a coefficient. In fact, we'll kind of redefine what that A is in terms of back all the way back to the definition. But if you've got y to the first and x to the second, that's going to be parabolic, right? Clearly not elliptical, and not hyperbolic. So we'll develop these equations, and we'll have another letter to stick in there instead of A that describes that parabola a little better. All right, so let's start with parabola. Definition of a parabola. Anybody know what is true about every point on a parabola in reference to other things in the coordinate plane? This may or may not have been a part of your pre-calculus class or advanced math class that you took in high school. It's a set of points in a plane equidistant from a given point. Is this ringing a bell at all?
Mm-hmm.
Did you have the definition in your prior math class? Set of points in a plane equidistant from a given point, which is called the focus, and a given line. Anybody remember that name? Directrix. Thank you. So, let's say the given point, the focus, is here at the point 0, P. And that means that because I want the origin to be on the parabola. So if it's on the parabola, that means I've got to come down here with the directrix. So the directrix, tell me what its equation would be if it's P units below the x-axis. y equals
Negative.
negative p. So where is the parabola? Well, let me see if I can put it where it needs to be. So there's our friend, the parabola. So if we're going to go back to the definition to generate the equation, which we are, then let's pick a point that is on the parabola and let's describe it so that it represents all points on the parabola. So we'll call it xy. What is true about any point that's on the parabola? This distance is equal to this distance. Is that correct? According to the definition? That point on the parabola is the same distance away from the focus as it is from the directrix. So, let's split this distance into two pieces. This distance, because the directrix is p units below the x-axis, that's got to be p. It's interesting that I took an antibiotic for 20 days and my cough is coming back just 2 days later. That's kind of interesting. How about this distance from the x-axis up to this point?
Y.
Y?
What?
Oh,
No.
y. Okay, so you're saying it's y. I thought you were asking why. Every point, it's up. If the coordinate is x, y, it's up y units. Is that correct?
Mm-hmm.
Everybody okay with y for this distance and p for this distance? This is a point, 0p, and this is a point x, y, so we can use the distance formula for that, which we will do. So we want to come up with an equation. See if I can keep that there. So the distance from the focus to the point, so we've got a distance formula for that. So that would be x minus 0 squared, y minus p squared. Does that look like the distance from the point on the parabola to the focus? Hope it does. And the other distance is y plus p. So that should be an equation, a mathematical sentence, that says the same thing that the definition said. Distance from any point on the parabola to the focus is equal to the distance from the point to the directrix. What could we do to simplify this equation? It's going to get a whole lot simpler.
Square both sides.
Square both sides. So if we square this square root, we get what's under the radical. X minus 0 squared is just x squared. And the right side will square that, and we get y plus p quantity squared. Let's go ahead and simplify. Maybe we can group together some like terms. Y minus p, the quantity squared, y squared minus 2p y plus p squared. Over here, y squared plus 2py plus p squared. We're going to be doing a lot of expanding and distributing and stuff today, so if I've got an arithmetic error and you see it, and the likelihood is pretty good, make sure we catch it before we go any further, because it'll really mess us up. Anything that we can basically strike from left side to right side.
P squared. Y squared.
Okay, they both have a p squared. We can subtract p squared from both sides. They both have a y squared. We can subtract that from both sides. Anything else that we can consolidate or put together?
Yeah, the 2py.
Add a 2py, which gets rid of that. So x squared equals
4py.
4py. And normally we're used to solving things for y, right? Mm-hmm. And the equation that I put up here earlier had it solved for y. So let's solve it for y. So y would be equal to what? 1 over 4p? Divide both sides by 4p?
Yes.
So there's our equation. What did we say earlier was going to be the equation for a parabola? We said it was going to be y equals a x squared. Don't we have that?
Yep.
We have now defined a in terms of, back to the definition, we have a as 1 over 4p, where what was p? P was the distance from the vertex to the focus. So in terms of p, we know that a value, that coefficient, is really 1 over 4p. So we derived the equation, in fact, I think a little bit better equation than what was on that sheet. It's a little more descriptive. If we wanted a more generic version of that, this has vertex at the origin. What if the vertex were somewhere else? Now, we're not going to go back and do the diagram. It's the same diagram, just shifted up or right or left or somewhere else in the plane. How would the equation look if the vertex of the parabola were at HK? What would that look like? Good. Go ahead. Instead of y, it's going to be
y minus k quantity is equal to 1 over 4p times x minus h quantity squared.
Does that sound right?
Yeah.
That ought to do it, right? So this is the same equation. This is a simplified version because the vertex is at the origin. If the vertex is somewhere else, just plug it in. Y minus k, x minus h, and you're in business. P is still the same thing. It's still distance from vertex to focus. And then go p units the other direction, and that will take you to the directrix. So let me get an example here. Y equals 1/2 x squared. Okay, that's not our simplest version. Y equals x squared would be kind of our simple parabola from our library of functions. We've got a 1/2 there. What is that 1/2 equal to?
1 over 4p.
1/4.
That 1/2 has to be 1 over 4p. So if that's true, p must be
2.
p must be 1/2 because 2 equals 4p, so p has to be 1/2. So the vertex, not that we sketch parabolas this way, but we could. The vertex is at the origin, and to get from vertex to focus, we would go up 1/2 of a unit. So if this is 1 unit, then we would go up 1/2 of a unit. We would go down 1/2 of a unit. To get to the directrix has what for its equation? Y equals negative 1/2. Is that correct? And I'll try to sketch it by making every point on the so this point, if it's actually a point on the parabola, this distance would be exactly equal to that distance. If this is a point on the parabola, this distance would be exactly equal to that. So I don't know if my diagram illustrates that very well, but if it were a very accurate diagram, that would be true. Questions on parabola? Yes?
So the definition of p can be extended from to not only the distance from the vertex to focus, but also from the vertex to the direct.
The other direction, that's correct. So P will carry a sign with it sometimes because we will see parabolas that open a different direction. So if the equation were to look something like this, then we know that parabola opens down, correct? Because of the negative lead coefficient. So negative 1/8 equals 1 over 4p. So if that were true, then p would be what? Negative 2. So we would go, so it does carry a direction with it. So we would start with our vertex here, and this time go down 2 units to get to the focus, which is 0, negative 2. So it is directed distance from vertex to focus. Is that all right? Yes, question.
What are we going to be like using this for? Because I've like never seen anybody use it with like the focus and the.
We can, one of the things we're going to do in calculus is, and I don't know that it does necessarily, I'm not trying to justify this, but here's a calculus problem that uses parabolas. So you will have a parabola, and you'll have a line graphed in the plane, and you'll be asked to find the area of the region between them.
Right.
Okay? So graphing, or a reasonable facility with graphing parabolas, I think is helpful.
So using the focus and the direction.
No, I probably honestly
Oh
wouldn't.
no, that's what I was asking. What are you?
It
using
just-
the focus and the director.
Just goes all the way back to the definition.
So you just like.
Right. So what is this thing that we call a parabola? It's actually a set of points that satisfies the definition. But if you were graphing that, you probably would not find the focus nor the directrix.
that's what I
You
was
would probably
thinking.
plot points.
Okay.
But we will certainly use parabolas later in this course. Nicole.
In the example that you just did, if you were to graph the directrix, would it be at positive 2?
Yes. P units, or in this case, negative 2 units the other direction. So the directrix would be right here.
That's crazy.
All right. Good question. So kind of useful, but not all that useful, to be honest with you. Ellipse. Ellipse is a set of points in a plane. Such that the sum of the distances from 2 fixed points is a constant.
From 2 what?
2 fixed points. And we'll call those foci. So we'll again start with a simple version, and that would be an ellipse that has its center at the origin, and we'll adapt it from there. So let's say the 2 foci are at negative c, 0, and the 2 foci will be on the major axis. So we're going to put them at c0 and negative c0. So this distance c will be the directed distance from the center to the focus. According to the definition, we've got this ellipse in the plane, and any point on that ellipse, so I'll just pick this point. That's kind of our generic point. When we finish with the equation, every x comma y in the equation would be a point that would satisfy the conditions of the ellipse, such that the sum of the distances from these two fixed points is a constant. So this distance plus this distance is fixed. And in fact, any point that I pick on the ellipse, the sum of those two distances is fixed. So we have distance from xy to negative c0. We can do that with the distance formula. Excuse me, distance from xy to z0. We can do that with the distance formula. This is a chore. Let me tell you that we're about to embark on a chore. So I'll kind of go quickly, and certainly if I make a mistake, correct me. But we want to start with the definition and get the distance from the two fixed points. So here is one of the distances, x minus negative c and y minus 0. From xy to c0, x minus c and y minus 0. So there's the sum of the distances from xy to the two foci, and it says in the definition that that is a constant. Okay? Because I know where we're headed with this, I could set it equal to k, but then we'd have this number at the end that is in terms of k. But I know where we're headed, and 2a is going to be helpful to us. The fact that I called this constant, and we don't even know what a is yet. But a will be a value that will be valuable when we're done. So I've got this, and I'm up here, and I get to choose. So I'm going to say the constant is 2a. It'll actually be helpful at the end. So does that seem to satisfy the conditions of the definition? Sum of the distances from two fixed points is a constant. Now I can clutter this diagram up because I'm about to move it away, but if I'd picked that point, this distance plus this distance would be the same number. It would still be 2a. This point on the ellipse, this distance plus that distance is also 2a. So whatever point you pick on the ellipse, the sum of the distances from that point that you pick to the two foci is fixed. So I don't know what it is for this particular sketch. It might be 15. The sum of those two distances is 15 from the two foci. It's some number, which we'll see here when we're done. Let me see if that makes it. I think that'll make it. Top of the diagram. All right, any indications of what we need to do to simplify this? Square both sides. And that's what I would say first. That's not going to work in this original form.
Some, right?
What would happen that would be absolutely hideous if we squared both sides in the form that they're in right now? You would be squaring this binomial, and when you square this binomial, don't they have a middle term?
Yeah.
And the middle term would be twice their product?
Yeah.
Don't think we want to go there. So let's move one of these to the other side. That's y minus 0 squared, so I'm just going to call it y squared. So I'm going to send this one over to the other side. It's still not delightful. But at least now when we square both sides, we don't have this completely hideous middle term. We have a semi-hideous middle term. So let's square this and square this. So the left side now, when we square a square root, we get what's underneath. This is a binomial on the right side. So when we square that, we get the first term squared. Here's the bad part, unfortunately. The middle term is twice their product. But the last term, everybody see where that's coming from? It's twice their product
Yes.
for the middle term. And then the last term is this last term squared, which is a square root squared. Everybody okay with that? Let's see if we can expand some things, get rid of some like terms. And because we still have a radical, we're eventually going to have to isolate that radical and then square both sides again. But let's see if we can get rid of some terms. X squared plus 2cx plus c squared plus y squared. Can't do much with this term yet. And here we've got x squared minus 2cx plus c squared plus y squared. Running out of room there. Running out of room, so we need to get rid of some terms. Do you see any terms on the left side of the equation that are exactly the same as the terms on the right side of the equation, so we can just strike them? X squared over here and x squared over here, gone.
C squared and y squared.
C squared and c squared, gone.
Y squared.
Y squared and y squared, gone. So we're basically subtracting those terms from both sides. Anything else that you can see might be advantageous before we isolate the radical and square again?
And the 2cx.
Okay, add 2cx. So that's gone. Minus 2cx plus 2cx, gone. And over here we've got 4cx equals 4a squared minus 4a.
Wouldn't you want to bring over the 4a squared too, so you can?
Yeah, we do now. In fact, maybe we can do two things at one time.
Divide them.
Divide everything by 4. So we'll divide the left side by 4. That's gone. Divide the right side by 4. Everything has a 4, so each term gets divided by 4. And let's bring the a squared over here. Actually, let's do this. Let's leave the a squared where it is. Let's bring the cx, which is here, over here. And then let's take this radical, which is negative over here, and move it to the other side so it's positive. So now we have isolated
Yeah.
A. Thank you. See, I told you, you better watch me. Something will disappear, and then we'll want it at the end, and it won't be there anymore. Thank you. We've isolated the term that has the radical. So let's square again, square both sides.
Can you divide by a?
We could,
Both sides?
but it would divide this term nicely, because the a would be gone. It would divide this term nicely. It wouldn't divide this term.
Okay.
So we have to be able to divide every term.
Okay.
And we're going to be able to do something like that, but not at this point in time.
Okay.
So let's square both sides. So we've got a squared, and then we're going to square this square root. And now we're going to square this side. First term squared, a to the 4th. The middle term, which ought to be twice their product. And then the last term squared ought to be what? C squared? X squared? I told you this was going to be a mess, right? It's kind of a mess.
Are we ever going to have to do something like
Will
this?
you have to do this
Test
problem?
quiz?
Absolutely not.
Oh.
Okay. Will I ask you to replicate what we're doing right now? Absolutely not. That's unfair. Okay. Now, could it be possible for like some extreme bonus on a test or quiz? Some of these things, like developing the equation, those might appear as a bonus.
Okay.
But as far as down the middle of the road, no. They are off in the ditch, not down the middle of the road. All right, let's expand things. So we've got x squared minus 2cx plus c squared plus y squared. Let's distribute the a squared to each of these. Okay, any consolidation of terms that you think will be helpful here?
Minus 2ac.
Okay, we do have like terms here. A squared cx term, we have minus 2 of them here. And do we have minus 2?
Yes.
Okay, so we can get rid of those?
Yep.
Wait a sec.
No, you
No,
can't
you
get
can't get
rid
rid
of
of them.
them. You would have to add one
Yeah.
of them. Because they're both negative.
Right, so if I add
Oh, yeah.
2a squared
Yeah.
cx to both sides,
That
I'll get rid
works.
of both of them. Is
Now
that
if they were
correct?
both positive.
Right.
Yeah, anything that's the same on both sides of the equation, basically we can undo that to both sides and it should be gone. Let's do this. Let's put all the variable stuff on one side, so I'm going to leave this. And by variables, I mean x's and y's, because that's what we're trying to do, is describe x's and y's on the ellipse. So a squared, x squared, I'm going to leave it here. I'm going to leave a squared, y squared over here. I'm going to bring this term from this side over to here, which now means it's minus, right? A to the fourth is still here, and this term, which doesn't have an x or a y in it, I'm going to send it to the other side, which makes it negative. Is that correct?
Right.
All right, did that account for everything that's left? Everything that remains, I hope, has been accounted for. Both these terms have x squared. These two terms have an a squared. And everybody okay with that? Just say, hurry up, Griggs, we're about done, so let's get out of here on time. See, that term appears twice. Let's make a substitution, which right now it's just plugging in a letter. Okay? Now, that letter at the end of this, when we're done, actually has some meaning. But where we see a squared minus c squared, let's plug in b squared. So I put in a b squared right there, and I put in a b squared right there. Divide all the way through the equation by a squared b squared. And if we divide every term by a squared b squared, b squareds are gone, a squareds are gone, a squared, b squared are gone. So we have x squared over a squared, y squared over b squared equals what? 1. Does that look familiar? That's a battle. I told you it was going to be a battle. Now, the question is, did we end up with the same thing?
Yes, we did.
The answer to that is yes, we did. There it is. X squared over a squared plus y squared over b squared equals 1. So that helps you to appreciate that little equation because it's a battle to get there. We're out of time, so we will pick up with examples of an ellipse, a couple of examples of a hyperbola tomorrow, and we will continue on.